So last time we studied the OP limit of the 4-point function, and today we'll focus on the OTOC limit, okay, the OTO limit. And then after that, I hope to get to deriving the Schwarzian action starting from a gravity theory, okay? So we claimed that the Schwarzian describes the low energy degrees of freedom in the SYK model, but I'll show that it actually is the surface term in the action of a two-dimensional gravity theory. And so there's a duality between the SYK model and JT gravity. Okay. Okay, so we ended with writing down the OP limit of the 4-point function, okay? And we could extract, remember, we could extract the dimensions of the operators that appear in the OP, okay? So the structure of the 4-point function could be written as follows. So it's a sum over 4-point function is a sum over m from 1 to infinity of cm squared times the conformal block with weight hm. And the dimensions hm, remember, were roots, right? These were roots of k, c, hm equals 1. Okay, so where we have an analytic expression for kc, so we can solve for these dimensions at least numerically. Okay, and we can actually parameterize the dimensions as 2 delta plus 1. Delta is 1 over q plus 2m plus epsilon m, where this remainder becomes small for large m, okay? Where epsilon m becomes small at large m. Okay, so epsilon m is actually proportional to 2m to the negative power, yes, this is actually going to be a negative power because delta is smaller than 1 over 4. Okay. Okay. So the asymptotic form of the dimensions sort of has a structure that looks like a 2-particle state. So you have 2 times the dimension of each Majorana fermion. But if you look at this remainder, it's order 1. The remainder is 1 plus 2m plus epsilon m. Okay? So it's different. If you had weakly interacting fermions in the bulk, you would expect the remainder, this anomalous dimension of the operators that appear in the OPE, to scale like 1 over n. So it would be suppressed in n, but these dimensions you can see have a remainder that is of greater than 1. So this tells us that the tower of states can't rise from a weakly interacting particle. Instead, you need a non-local theory, in particular a string theory, with a string scale that is not suppressed in the compared to the ADS radius. Okay, so spectrum. So shift in dimensions. Shift in dimensions is of order 1. Not 1 over n. Okay, so it cannot result from weakly interacting fermions. Instead spectrum looks like string theory with string scale that is of order ADS radius. String scale of order ADS radius. Okay. So if you consider the full SYK model, basically the dual theory is expected to be non-local, but JT gravity, the part that I'll describe later, just captures the low energy degrees of freedom, the soft mode, the reparameterization degrees of freedom that I described earlier, and that can be treated locally. So let's now turn to the parametrically large part of the 4-point function that the non-conformal part that we left out last time. Okay. So I mentioned that there are two ways of calculating the non-conformal part. You can go through the analysis of deriving the non-conformal correction to the Green's function, and then to the correction to the kernel, and then to the correction to the eigenvalues and so on, and plugging in everything into that summation formula we had for the 4-point function. Or you could sort of use an effective field theory approach and use the Schwartzian action. Okay, so I'm gonna take the second route in this lecture and derive the large part of the 4-point function using the Schwartzian action. So from an effective field theory point of view, okay, parametrically large part of 4-point function, the non-conformal part, arising from non-conformal perturbation, arising from non-conformal correction. To the Green's function. It takes the form large, tau 1, tau 2, it's given by delta G, by R, tau 1, 2, delta G, so delta G is delta G IR arises from reparametrizing the Green's function. So the origin of perturbations would be the solution to the equation of motion. Okay, so for example, if you write down the Schwartzian action and you vary the action with respect to phi, right, the angle degree of freedom, you'll find that the solution gives you phi of tau equals 2 pi tau over beta. So this is the classical solution. And then a reparametrization away from this classical solution is what I'm denoting delta G IR here. Okay, so it's a perturbation to the Green's function coming from IR degrees of freedom. And these perturbations will interact via the Schwartzian. So if we derive the propagator for these phi's from the Schwartzian and compute this correlator using the propagator, we'll actually get this parametrically large term, which goes like beta j over n. Any questions? 혹시 온도 좀 내려주실 수 있어요? 좀 더워가지고. 네. Okay. So this expectation value involves a functional integral over phi, the soft mode we described previously. Okay, so expectation value involves functional integral over, okay. So imagine doing a path integral over phi, soft mode degree of freedom. Okay, so recall the definition of phi. Okay. This is how phi of tau relates to delta G. Phi. Okay, f of tau is constant e to the, okay, with the action, okay, remember the Schwartzian action. So the effective action is minus some constant times large N, J inverse 0 beta d tau, Schwartzian of e to the phi tau, tau. Okay. There's Schwartzian. Okay. Schwartzian of f of x. Okay. Well, we wrote down the definition earlier. Hopefully you can look that up. Okay. So to make things easy for ourselves, we'll factor out the SL2R invariance from the beginning. So recall that there's an exact SL2R symmetry of the action. That's a gauge symmetry in our path integral. So to deal with that gauge symmetry, what we can do is instead of phi itself, we can start out by defining an SL2R invariant version of the variable. So using the SL2R invariant variable, invariant observable, O theta is Schwartzian e to the phi theta. Okay, so theta is 2 pi tau over beta. Okay. So instead of using the time tau, we've just switched to using theta as our time. And then the Schwartzian is itself, as I mentioned before, is SL2R invariant. So we can just view this as the variable for which we are going to compute the 2-point function. Okay. So using this variable, we can actually write, if you just compute delta G using this formula. So this gives you the perturbation away from the classical solution. And this is actually a nice exercise that you can express the perturbation of the Green's function as follows. So 2 pi over q, theta 1, theta 2, 2 pi. So theta ij here is going to be 2 sine of theta I minus theta j over 2. Okay. So we basically expressed the perturbation in the Green's function as an integral over this SL2R invariant perturbation. Okay. And then we can plug this into the 2-point function here and then express this parametrically large contribution as an integral over the 2-point function of this SL2R invariant observable. Okay, so let's plug in this equation into here. Okay, so plugging in into star into star star. We have F large over N is equal to the conformal Green's function multiplied. Okay, multiplying it an integral over intermediate times. Okay, we have, okay, the form of this, this factor is basically a conformally invariant 3-point function. And then you six over. Okay. So all we've done is express the 2-point function there as an integral over the 2-point function of O, delta O. Okay. Any questions? 아, 맞아. 이거는 이 파이는 classical solution. 네. 이거요? 이거는 이 식에서 바로 나와요. 그러니까 파이가 주어지면은 g가 주어지잖아요. 저 식에 의해서. 그러니까 델타 파이. 그러니까 파이를 파이 클래시컬 플러스 델타 파이로 놓은 다음에 파이에 의해서 g가 정해지는 저 식에 집어넣으면은 델타 g를 이런 식으로 표현할 수가 있어요. Okay. So we only need to compute the 2-point function of delta O, okay, which we can do from the Schwartzian action. So we expand the Schwartzian action around the classical solution and we find the propagator is given by the following. derive a propagator delta O theta 1, delta O theta 2 is beta j over curly j over 4 pi squared alpha Sn. So here's the parametrically large factor, beta j over n, which will appear in the final 4-point function. And then we have m not equal to 0, m squared to the I. Okay, and in position space, this is just minus 2 pi times second derivative of delta function plus delta function plus 1. Okay, so why do we have this factor beta j over n, which is kind of important? Where did it come from? It came from here. If you look at the effective action scales log n over beta j. So there's a large n there, and the Schwartzian goes like the second derivative. It has 2 powers of differentiation with respect to the time. So overall, this action is going to scale like 1 over beta. So the entire effective action scales like n over beta j, and that's why when you compute the propagator, you get the inverse of that factor, which is beta j over n. Okay. So plug in this propagator inside this integral here, and we are done. We have the part of the 4-point function that arises from the fluctuation of the IR degrees of freedom. Okay. So using this, using this propagator, we can perform the integral star, star, star. Okay, and the result is as follows. Again, the result is different between the OP and OTO region. And I'll write down the expressions in both regions. And F large is, okay. So we have the factor beta j over, some numerical factor here, times 1 minus theta, 2tan theta over 2, times 1 minus theta prime over 2 tan theta prime over 2. So this is in the OPE region. So notice in the OPE region, the 4-point function only depends on the difference between the 2 times here. So theta is theta 1 minus theta 2. And remember, theta is related to tau by theta equals 2 pi tau over beta. Theta prime is theta 3 minus theta 4. And in the OTO region, we're actually going to have a dependence on the difference between the center of the 2 times. So we're going to have a dependence on theta 1 plus theta 2 over 2 minus theta 3 plus theta 4 over 2. So the expression in the OTO region is given as follows: minus pi times sine of delta theta plus over 2 sine theta over 2 sine theta prime over 2 minus pi times pi minus 2 delta theta prime over 4 tan theta 2 tan theta prime over 2. Oops. Then plus 1 minus pi minus theta 2 1 plus this is the OTO region. Okay. So now we are interested in analytically continuing this result in the OTO region in particular to real times. And that's where we'll see the exponentially growing chaotic behavior of the OTOC. So let's recall what's happening here. So what's the definition of F, right? F gives us the subleading part in N of a Euclidean time-ordered 4-point function, right? So remember, we had 1 over n squared, sum over ij of Euclidean time-ordered Majorana fermion at tau 1, tau I, tau 2, chi j tau 3, chi j tau 4, okay? And this was, okay, some leading part plus 1 over n, so some order n to the 0 part plus 1 over n times f tau 1, tau 3, tau 4. And we're looking at the part in F that goes like beta j. So we're looking at a contribution to the Euclidean time-ordered 4-point function that goes like beta j over n. Okay, so the beta j is here. And it is given by the conformal 2-point function, product of conformal 2-point functions, multiplying these functions. And the first expression, the OPE region, corresponds to the, if you remember the ordering of the times. So because of the Euclidean time ordering, right, depending on the ordering of the times, you'll have a different ordering of the operators inside the correlator. So for an OPE ordering, you're looking at because of the time ordering, you're just looking at this this kind of function, right? So for example, this would be the ordering of operators when tau 1 is greater than tau 2 equals greater than, okay? So if I just draw a picture in the complex t plane, so in the complex time plane, right? This is the real axis corresponds to real times, and the Euclidean time tau corresponds to the imaginary axis, right? So when tau 1 is greater than tau 2, is greater than tau 3, is greater than tau 4, they're ordered in the complex time plane as follows. You have tau 1 here, and then, sorry, 1 here, 2, 3, 4. Okay. And we have okay, so they're placed on this time circle here. You should, okay, this is 0. So this point corresponds to Euclidean time equals 0, right? And Euclidean time equals beta corresponds to some point below, and we should really think of them as being connected because there's a periodicity in Euclidean time. And when we analytically continue Euclidean times to real times, the important point is that we have to preserve the ordering of the times along the vertical axis. Okay? So that's why it's important to start out with the right Euclidean ordering in order to go to the OTOC. So the OTOC, standing for out of time order correlator, corresponds to an operator in real time where the fermions inside the correlator have an IJ ordering. Okay, so OTOC, out of time order correlator, okay. In real time, you want a correlator that goes like chi I, okay, some operator at t, and roughly the same operator at times that are approximately, okay, so, and then you have a different fermion at time equals 0 and time, okay? So these two times don't have to be exactly the same. They can be approximately at some large time t. And then you have another pair of fermions at an earlier time. Okay, so this is what is meant by out of time ordering. So 네. 네. 둘 다 트리플 스타에서 나온 거예요. 그러니까 이 인테그럴을 계산할 때 그 결과가 바뀌는 거예요. 왜냐면 저 theta 5, theta 6에 대해서 인테그럴을 계산할 때 바뀝니다. 네. 제 그 논문, 키타이브랑 쓴 논문에 보면 이 부분이 나와요. 어떻게 하는지. So does everyone, OTOC에 대해서는 다 이해하셨어요? OTOC가 뭔지? Everyone understand how this is different from a regular time-ordered correlator. So what's a time-ordered correlator? Time-ordered correlator means that you have to order the operators according to time, right? So the operators with larger time, you would have, if we time ordered this, you would have chi IT, chi J0, chi J0. 네. 그쵸. 이 두 개가 사실은 그냥 small time이고 이 두 개가 large time이라고 생각하시면 돼요. So when you use Feynman rules, so suppose you started out with Feynman rules in real time, and you wanted to compute a correlator. So we only have a prescription for calculating the time-ordered correlator in the usual diagrammatic method, right? When you compute Feynman diagrams in real, for example, in free field theory at zero temperature, what kind of propagator do you use in the Feynman diagrams? 아는 사람, what kind of propagator? time ordered propagator를 사용하잖아요. Feynman propagator라고 하죠. 그 Feynman propagator를 사용해서 다이그램을 계산해서 얻는 결과는 어떤 종류의 correlator를 계산합니까? 역시 time ordered correlate를 계산하게 되는 거예요. 마찬가지로 우리가 유클리디안 시그니처에서 계산을 했잖아요. 파인먼 다이어그램을. 거기서 유클리디안 타임 오더드 프로퍼게이터를 계산하게 되죠. 그래서 사용하는 프로퍼게이터도 유클리디안 타임 오더드 2-point 펑션을 사용해서 계산을 했어요. Okay? So the non-trivial part is that we do all our calculations in Euclidean signature and get results for the Euclidean time ordered correlator, but the result differs according to the time ordering in Euclidean signature. But we have to analytically continue the OTO from the OTO region, because in the OTO region, our ordering of operators in Euclidean time is not 4, 3, 2, 1. It's going to be 4, 2, 3, 1. So this is the ordering in the OTO region. And this is the OPE region. So the OTO region corresponds to an ordering of operators along the imaginary axis that goes like 4, 2, 3, 1, for example. Okay? Now, because we have to preserve this ordering along the imaginary axis when we analytically continue. That's the rule for being able to analytically continue. You can't change this ordering along the imaginary axis. We have to continue from the OTO region in order to get this kind of correlator in real time, because you have the side index is kind of important. It's only when we have an ordering 1, 3, 2, 4 that we have an alternating IJ configuration. Okay? So this is the OTO region. Now, when we analytically continue this Euclidean time ordered, this Euclidean time ordered correlator in the OTO region, the picture is as follows, okay? You can, for example, analytically continue tau 4 to tau 4 plus I T4, where T4 is large. So, and then you can continue tau 3 to tau 3 plus IT, where does this make sense? This is the kind of picture that represents the analytic continuation that we perform, starting from the OTO region. Okay, so the times are here inside the theta variables, the taus, and we, for example, analytically continue tau 4 and tau 3 inside this expression to real times. And because of this factor, because of the sine delta theta plus factor, we are going to get an exponentially growing piece. Okay? So what happens when you analytically continue sine of some Euclidean time to tau, when you continue tau to IT? You get a sinh function, right? So that sinh function is exponentially growing in the time difference between the 3-4 pair and the 1-2 pair. So that's exactly the exponentially growing piece that we're looking for. Okay. 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 So I'm just going to do a different analytic continuation where I continue 2 and 1 to large times and keep 4 and 3 at small times. So I'm going to analytically continue tau 2 here and tau 1 here. So I've continued, okay, so this analytic continuation is So we do the analytic continuation. Tau goes to IT, and tau T1 and T2 we take to have a large T component. So you can basically take the Euclidean time separation between all the operators to be infinitesimally small. Okay, so you have some regulator in Euclidean time. So you preserve the ordering, but the separation is infinitesimally small, and so the complex time is real, okay, if you ignore the effect of the regulator. The regulator only comes in the ordering, okay, where T is much, much greater than beta. Okay, and we take T3 and T4 to be approximately 0. Okay. And then we have F large. After this analytic continuation, we have F large tau to tau over n is beta j over 4 pi alpha Sn, where E. So we have this exponential factor. So I'm still using Euclidean times here. So I have an I here, but this exponent will become large when we analytically continue to real times. And okay, so we have 2b. So b is a constant. B is a constant that I wrote down in the first lecture involving q. Beta 1, 2 minus 2. 2b 1 over q. Beta 3, 4 minus 1. Okay, so hopefully you can see that with this analytic continuation, we have an e to the 2 pi over beta times t coming from this factor. So this goes like beta j over n times e to the lambda L t, okay, where lambda L is the Lyapunov exponent, which is 2 pi over beta. Okay. So the out of time order correlator OTOC exhibits exponential growth in the separation between the times 1, 2, and 3, 4. Exhibits exponential growth. With a Lyapunov exponent. Okay, so note that this growing piece resulted from the dynamics of the reparameterizations, right? Came from the dynamics of soft modes governed by the Schwartzian action. And the growth actually saturates at a certain time scale. So we got these, we got this expression, if you think about it, from ladder diagrams, okay? But at some point, we have to include diagrams that are subleading in beta j over n. Okay, so we were looking at the 1 over n part of the 4-point function, and we found the scaling. We found a piece that goes like beta j over n times e to the lambda t. Now, for sufficiently large t, though, what happens to this factor? When t becomes sufficiently large, this factor will become of order 1, right? For small times, it goes like beta j over n. right, which is small in our regime of parameters, where beta j is much smaller than n. But if you wait sufficiently long, the exponential factor grows, and so the entire thing goes like order 1, okay? So the exponential, what happens at that point is that you need to also take into account terms that are here, okay? So if you look at the 1 over n squared piece, it will have basically, there'll be a scaling that goes like beta j over n times e to the lambda lt squared. And when this factor becomes of order 1, these are no longer suppressed compared to the beta j over n times e to the lambda lt terms coming from the 1 over n piece. Okay? So the exponential growth actually saturates. What happens at the exponential growth of the OTOC saturates when beta j over times n times e to the 2 pi t over beta is order 1. Okay, so at which point ladder diagrams no longer dominate, and you have to take into account multiple ladders. Okay, so I'll draw what a multiple ladder looks like. Okay. Diagrams no longer dominate, at which point let no longer dominate. Okay, one has to include multiple parallel ladders. Okay. So recall the ladder diagrams we had in the 1 over n piece in the 4-point function were of this form, right? They look like this. So this is one ladder. Now, if you go to 1 over n squared, for instance, you'll have Feynman diagrams that have two parallel ladders like this. And each ladder scales like beta j over n times e to the 2 pi t over beta. So this diagram goes like that factor squared. And so on. When this is of order 1, you cannot ignore diagrams with three parallel ladders like this, right? Okay. So, 네. 그러니까 이 order 1이 되는 지점을 우리가 scrambling time이라고 해요. 처음에는 그쵸? 그 scrambling time이 어떻게 될까요? order 1이 되는 지점이 어디예요? T가 beta over 2 pi times log n over beta j 되는 그 시점이 되겠죠. 그걸 scrambling time이라고 하고, scrambling time 그래서 scrambling time 이전에는 이 exponential growth를 볼 수가 있다. 근데 scrambling time 되면은 saturate 하면서 이런 다이어그램들이 중요해진다. 네. 네네네. 네, 그 이후에는 우리가 계산한 이 결과가 4-point function에서 dominant한 부분이 아니라는 거죠. accurate하지 않죠, 우리가 계산한 결과가. 그렇죠? 왜냐하면 1 over n squared part에서도 비등한 contribution들이 나올 거니까, 그렇죠? Okay, so one can argue, and this is called the bound on chaos, that this exponent 2 pi over beta is the maximal exponent that you can see in a large and chaotic quantum system, right? So you can imagine just having an arbitrary quantum system, for example, in 0, 1 plus 1 dimensions, just like the SYK model, right? And you can imagine computing the 4-point function and analytically continuing and so on. And at finite temperatures, in general, you will find some exponent here. Okay? So the intuition of where this exponentially growing behavior comes from is connected to the idea of chaos in classical dynamical systems, right? So chaos actually refers in classical dynamical systems, refers to the fact when you have a phase space, for your dynamical system, and you start out with two initial conditions which are nearby. As you evolve the system forward in time, the trajectories in phase space diverge. And this divergence is exponential in time. Okay, so this is where the terminology Lyapunov exponent originates. When you have a chaotic dynamical system in the theory of classical dynamical systems, you have something called the Lyapunov exponent. But what we've done here is we have sort of we started out with a quantum system with a large number of degrees of freedom, right? And we derived this exponent, which was originally defined for classical systems, right? So we can sort of imagine that the physics where this comes from is sort of a semi-classical equivalent of this picture. So you start out with, we started out with a small perturbation, right? So the picture is as follows. The OTOC, what kind of physics is the OTOC capturing? So imagine, okay, so this is a picture of the SYK model in time. Okay, and we have to imagine that it actually lives, on the boundary of ADS2. So remember I drew this picture. We have ADS2, Lorentzian ADS2, and the SYK model we should think of as living on some boundary here. Okay, some curve. Okay, so at time equals 0, what we can do is apply an operator. So we start out with a thermal state for the SYK model, and then we apply a fermion operator at time equals 0. In the gravitational picture, that sends in some perturbation into the bulk. Okay. So in the dual gravity theory, we actually have a black hole in JT gravity, and we imagine we send in some perturbation. Okay, send in some perturbation here. Now, there's this fact that the energy of this excitation undergoes a blue shift, right? So people are familiar with the idea that in gravity, there's a redshift, right? What does the redshift describe in a gravitational theory? You have a classical particle, right? And in a space-time with a killing symmetry, that classical particle has a conserved energy, right? So it has a conserved energy, but you can also think about, if you think about emitting a particle and then measuring, okay, you can think about emitting a photon, right? And then measuring the wavelength of that photon at two different locations. So you emit the photon at one point in space-time, and then you receive the photon at another point in space-time, right? And what does the redshift describe? if you emit a photon in the interior of space-time, when you measure that photon at the boundary of space-time, it'll undergo a redshift. The wavelength of the photon will be large, right? So the blue shift describes the opposite effect, which is that when you release an excitation from the boundary and measure the effective energy of the excitation from the point of view of the boundary. So imagine an observer that keeps on evolving at the boundary. So we use the Schwarzschild time t, and we measure the energy of this excitation in the local frame of the excitation. But there's an ambiguity in the definition of the local frame because you can boost a local inertial frame, right? You can boost a local inertial frame, and it's still an inertial frame. So you have to pick a reference frame, and the right reference frame to pick. There's a right reference frame to pick such that the local energy measured in that reference frame represents the effective energy as seen from the point of view of the boundary. So, okay, so what happens is that, think of this reference frame here. Okay, so the boundary observer carries a reference frame which rotates, right, in Schwarzschild time. If you think about a local inertial frame carried by the boundary observer. Okay, so let me draw. Okay, so at time t equals 0, the appropriate local frame, describing the observer is upright like this. But at a later time, the local frame rotates or gets boosted like this. So when you release this excitation in the bulk, and you measure the energy of this excitation in a frame that's rotated to be connected to this frame at later time, the energy of that excitation will actually be boosted. It's blue shifted. And the factor by which it is blue shifted is exactly e to the 2 pi over beta t. Okay? So this is sort of the classical intuition for why we should have an exponential growth, but there's actually a gravitational interpretation of this exponential growth, which is that it results from the blue shift of the effective energy of the particle as seen from the boundary observer. Okay? Because of this blue shift in the frame of the boundary observer at late times, the particle carries a very large energy and so creates a shock wave. You have to take into account the back reaction of the particle on the space-time metric. So this is a piece of physics that was first described by A. 't Hooft. So A. 't Hooft and I guess his student wrote a paper describing shock wave solutions in gravity. And it was pointed out that when you release a particle from the boundary, even if it's a very small, even if it carries a very small energy, at later times, the energy of the particle is blue shifted from the point of view of the boundary. So you should think of in the reference frame corresponding to the observations of at late times, you should think of a shock wave in the bulk geometry. And this is related to the fact that small perturbations that fall into the black hole will actually leave an imprint, right? Small perturbations will create a shock wave at large times, so it leaves an imprint on the geometry. And so in the SYK model and in general, in general theories of gravity, in general quantum theories that are dual to gravity via ADS-CFT, you can see this Lyapunov exponent. Okay. To be more precise, you need an Einstein Einstein gravity theory in the bulk to see this maximal 2 pi over beta. When you include stringy corrections, for instance, that exponent will decrease by a small amount. 네. 네. 그러니까 먼저 코릴레이터 보면은 conformal symmetry가 있었죠. 거기서 이미 symmetry가 매칭이 되죠. ADS2 제가 지난번에 말했죠. ADS2에 아이소메트리가 있다. 아이소메트리가 SL2와 아이소메트리다. 그래서 이미 symmetry 레벨에서 매칭이 되고 코릴레이터에서 매칭이 되고 그 다음에 또 어디에서 매칭이 되겠어요? 엔트로피 계산에서 매칭이 돼요. SYK 모델에서 이제 프리 에너지 계산해서 엔트로피를 구할 수 있거든요. 그러면은 이제 zero temperature 엔트로피가 있어요. 근데 블랙홀도 이 zero temperature 엔트로피가 있거든요. 이 ADS2지만 이 ADS2 geometry가 어떤 식으로 arise 할 수 있냐면 higher dimensional black hole에서 시작해서 그 black hole throat라고 하죠. horizon에 가까이 다가가는 그 부분의 geometry를 확대해서 보면은 그 부분이 ADS2 cross some other compact factor로 이렇게 나오거든요. 거기서 ADS2 geometry가 나오는데 그런 관점에서 보면은 zero temperature 엔트로피가 있어요. 그 zero temperature 엔트로피 위에 있는 그 하여튼 excitation을 지금 describe 한다고 보시면 되고 그 다음에 그 zero temperature가 엔트로피가 있고 그 다음에 low temperature limit에서 T에 비례하는 엔트로피가 또 있어요. 그 엔트로피가 중력에서도 엔트로피를 계산할 수 있겠죠. 랑 매칭이 돼요 또. 근데 그게 매칭이 되는 이유는 결국 슈워츠이언 액션이 같기 때문인데 제가 지금 이제 슈워츠이언 액션이 JT gravity에서 어떻게 오는지 말씀드릴게요. Okay, so besides the Lyapunov exponent, we have many different signs that the SYK model is dual to JT gravity, right? So one is just the form of the correlators because the 2-point function, for example, has conformal symmetry, right? That's one point. And then another point is you look at the thermodynamics. So you look at the scaling of entropy as a function of temperature, and you have a zero temperature piece and a piece that is linear in, you have a piece that is linear in T, away from T equals 0. So that matches also with calculations from gravity. 네. 네. 그러니까 gravity theory에서 알 수 있죠. 네, 블루 시프트가 있다는 거예요. 네. 네네. 네. ADS2뿐만 아니라 그냥 ADS, 그냥 gravity theory, 모든 gravity theory, 모든 디멘션에서의 아인슈타인 gravity theory는 2 pi over beta라는 엑스포넌트를 가지게 됩니다. 왜냐면 이 블루 시프트가 유니버설한 피노미넌이거든요. horizon, 블랙홀 horizon으로 떨어지면서 가는 이 블루 시프트가 이 베이타가 어디서 와요? 블랙홀의 템퍼처에서 오겠죠. 이게 유니버설하기 때문에 Any other questions? So the question is, yeah, does this only apply to, if you have a quantum system that is dual to, for example, ADS2, you should be able to see this exponent, but actually the physics of this blue shift is universal, and in particular, it applies in higher dimensions as well. So whenever you have a quantum theory in any dimension that is dual to Einstein gravity, you should be able to see this 2 pi over beta exponent in the out-of-time autocorrelator. Okay, so let's, I want to try to show you how you can derive the Schwartzian action starting from JT gravity. Okay. So not only can we compute the OTOC and see the physics of the the shock wave and so on. But at the level of the action, you can just directly derive the Schwartzian action starting from JT gravity. So JT gravity. Okay, so in 2 dimensions, so why JT gravity? So Jakiv and Teitelbaum first wrote down the action for JT gravity, and their reasoning was as follows. So in 2 dimensions, if you just write down Einstein's action, okay, minus 1 over 16 pi g Newton times d squared gr. It's a surface term. This computes the Euler characteristic of your space-time manifold. Okay, so is a surface term. The curvature of the Ricci scalar computes the Euler characteristic of your space-time manifold. Okay. The Euler characteristic, which is a topological invariant. Okay. So you don't have any dynamics. So Jakiv, if you look at the paper by Jakiv, the simplest non-trivial action for gravity in 2 dimensions, they decided you can get by just inserting a dilaton field in the action. Okay. So it was proposed by Jakiv and Teitelbaum. Simplest non-trivial dynamics and 2D gravity. Is given by the action. Minus 1 over 16 pi g Newton times. So you insert a scalar field, which is called the dilaton. Okay, there can be many conventions for defining the scalar. For example, you can express it as e to the some non-zero field, some real field sigma. But in general, this phi we think of as being positive for physical solutions, because we imagine it descends from a higher dimension. You can imagine that it descends from a higher dimensional theory, and phi is the codimension to area. Okay, so but phi, okay, is some scalar field. Is a scalar field, the dilaton. Okay. And of course, G mu nu is the two-dimensional metric. Okay, so this is JT gravity. So if you look at this action, phi just acts as a Lagrange multiplier, right? Because it only appears linearly. So if you think about doing a path integral over phi, you just integrate it out, right? And the constraint r minus 2 lambda is exact. It's not just a classical equation, it is exact in the quantum theory. Okay? So phi enforces the constraint that r is 2 lambda, where lambda is a cosmological constant. It can be 0, negative, or positive. And you can also vary the action with respect to the metric of the 2D metric, and you get an equation for the dilaton. So phi acts as a Lagrange multiplier. Enforces constraint at r minus 2 lambda is 0. Okay. While varying, and varying with respect to the 2D metric, respect to g mu nu, gives equation for the dilaton. Okay, so the equation is d mu d So I won't go into detail, but the action of JT gravity is also natural from the point of view of dimensional reduction. You can start out with Einstein gravity in 3 dimensions, and you can dimensionally reduce a 1 dimension, and you'll be able to arrive at the JT action. Okay, so we are interested in the case where the cosmological constant is negative. Okay, so let's assume a negative cosmological constant, which means that we have anti-de Sitter space, right? We have a space-time where the curvature, the scalar curvature, is constant at each point. Okay, so locally, the space-time is fixed. Again, the only thing that that matters will actually be the topology. So we've gone back to a situation where if you look at this bulk action, it's trivial, right? It just vanishes because of the constraint. But when you have a boundary, when your space-time has a boundary, in order to make the variational problem well defined, you need to add a surface term called the Gibbons-Hawking term. What does it mean to make the variational problem well defined? It means when you compute the variation of the action with respect to the metric, you will see total derivative terms. So that total derivative term needs to be canceled by the variation of a boundary term in order to make the variational problem well defined. So the appropriate boundary term that cancels the surface term resulting from varying the bulk action is called the Gibbons-Hawking term, and it involves the extrinsic curvature over the boundary. Okay? So in JT gravity, we have to add a boundary term that is given by the dilaton multiplying the extrinsic curvature. Okay, so we have to add a boundary term in ADS, okay, or in any space-time with a boundary. In ADS, we add a boundary term analogous to usual Gibbons-Hawking term. So the Gibbons-Hawking term is given by the integral over the boundary of the extrinsic curvature, and in JT gravity, we are going to add a term that is given a boundary term with density dilaton multiplying the extrinsic curvature. So we had a boundary term analogous to usual Gibbons-Hawking term. Usual. Okay, so I described to you the idea that you need to make the variational problem well defined, but of course the variation, the total derivative term in the variation that you get will differ depending on which boundary condition you impose on the metric at the boundary, right? So for example, if you impose a Dirichlet boundary condition, the terms in the variation that are proportional to fluctuations of the metric will vanish. So the surface term the boundary term that you need to add will depend on the boundary condition that you impose on the metric, but the kind of default choice is to impose Dirichlet boundary conditions on the metric, and the corresponding term that you need to add is the term that I described involving the extrinsic curvature. So you impose Dirichlet boundary conditions on metric. Okay. Okay. So with the inclusion of this boundary term in JT gravity, we have IJT. Okay. Now the action is no longer trivial because of the boundary term. -1/16 pi g Newton. We have the bulk action, which vanishes identically. And then we have a boundary term, which needs to be needs to be multiplied by a factor of 2 relative to the bulk term, and is an integral of phi k, where k is the extrinsic curvature. Okay, where the equations of motion, okay, where E, O, M are consistent with imposing. So not only do we impose Dirichlet boundary conditions on the metric, but we also fix the value of the dilaton on the boundary. EOM are consistent with Dirichlet boundary conditions on the dilaton field phi and G mu nu at the boundary of the manifold. Okay. So I'll just write down the definition of the extrinsic curvature for a general hypersurface. And in 2 dimensions, the computation of the extrinsic curvature becomes relatively simple. So note K. And it's actually this boundary term that will turn into the Schwartzian action when we actually compute the extrinsic curvature explicitly. So note K is the extrinsic curvature. A is extrinsic curvature of the boundary. Okay. For a hypersurface in general dimensions, K is equal to, okay, H is the induced metric on our surface. E A alpha, E B beta, these are projections, projective vectors. And we have the derivative of the normal vector. Okay, so E to the A alpha is defined by taking derivative of external coordinates. So these alpha are indices for coordinates in the larger space-time in which the hypersurface is embedded, and the A's index intrinsic coordinates that parameterize your surface, right? So imagine a surface in some larger space, a surface of one less dimension, a hypersurface in a space-time. And we have some coordinates x alpha in the bulk, and we have some intrinsic coordinates y a along the surface. So the y's, so the x's, right? The x's are going to be functions of y's on the hypersurface. And these projection vectors are given by taking the derivative of the bulk coordinates with respect to the intrinsic coordinates. Okay, so extrinsic coordinates. These are intrinsic coordinates. Okay, and HAB is the induced metric along the surface. E mu A, E nu B. Okay, this is the induced metric. So in 2D, 네? 네? 노멀, 네? 아, 노멀 벡터예요. n은 노멀 벡터예요. 네, 네, 네. 이거는 이제 이렇게 하면은 EA 알파 근데 이걸 바꿀 수가 있어요. 자유자를 바꿀 수가 있죠. 그 알파는 G 알파 베타를 이용해서 바꾸고 이제 A는 HAB를 이용해서 내렸다가 올렸다가 하는데 EA 알파 그다음에 어떤 벡터 V 알파 하면은 이제 프로젝션이 되는 거죠. 그러니까 프로젝션을 해주는 부분이고 이제 n이 normal vector. So n is the normalized normal vector to the hypersurface. Okay. So in 2 dimensions, running out of time. The boundary, this hypersurface is actually a curve, right? It's one-dimensional. And you can actually compute this extrinsic curvature as follows. Okay, so in in 2D, okay, so you have some curve, okay, and at each point along the curve you have some tangent vector x dot, and you have a normal vector n, and you can compute x nu d nu x mu. So what is this? This is like the change. This is like the covariant change of the tangent vector along the curve, and it's proportional to the normal vector. So this is always true in 2 dimensions. And the constant of proportionality is the extrinsic curvature of the line. Okay? So this is how you compute the extrinsic curvature of a curve in 2 dimensions. And the claim is that this phi k term here, when you compute the extrinsic curvature on an ADS2 background, okay? So because the curvature is fixed at each point, the Ricci scalar is fixed at each point in space-time, locally, your space-time is fixed to be exactly ADS2, okay? So, and furthermore, if you fix for convenience, we can, to leading order, because if we have a different topology, so this is the simplest topology you can have, the topology of a disk for a Euclidean ADS spacetime, right? If you have a non-trivial topology, right? Something like if you have multiple boundaries, for instance, that'll give rise to an action which suppresses the contribution of the geometry to the path integral by e to the 1 over g Newton, right? E to the minus some positive over g Newton. Okay, so basically the contribution of these non-trivial topologies to the path integral is suppressed by, is non-perturbative in 1 over g Newton. So if we're interested in the perturbation theory in powers of g Newton, then we can restrict ourselves to this trivial topology. And so then our space-time is entirely fixed, right? Locally, it's ADS2, and globally, the topology is a disk. So we have a fixed, furthermore, so we have a fixed metric, right? We have a fixed metric on this disk, which is given by 4 times dr squared plus r squared d phi squared over 1 minus r squared. So on this fixed geometry, we can compute this extrinsic curvature of some curve. Okay, put a curve. S1 크로스 그거는 2dimensional이잖아요. 아니 그 토폴로지가 이런 식이거든요. S1이 아니라 바운드리가 두 개가 있어요. 이거는 로렌치안 시그니처에서. 그러니까 로렌치안 시그니처에서는 ADS2가 이렇게 생겼고, 글로벌 ADS2가 이렇게 생겼고, 그 다음에 이 슈워실드 패치가 이 유클리디안 하이퍼볼릭 디스크랑 애널리틱 컨티뉴에이션으로 이제 연결돼 있어요. 여기서 이제 R이랑 여기서 파이를 IT로 컨티뉴 하면은 이 슈워실드 패치가 됩니다. Yeah, so the claim is that when we compute the K, the extrinsic curvature along a curve for a curve in ADS2, and we take the limit of the curve going to the boundary of this disk, we actually recover the Schwarzian action. Okay? So I don't have the time to go into this derivation in detail, but the picture is we have the hyperbolic disk in 2 dimensions, and we have some curve on the hyperbolic disk, okay? So in order for our theory to correspond to having a temperature in the SYK model, okay, so I'm now thinking of the SYK model, but basically I drew this picture before, right? I said that the phi degree of freedom in the SYK model corresponds to the angle here of a curve living on the hyperbolic disk. And I've gone to the same picture. Now I want to compute the action, this boundary action, phi k, for a curve in ADS2. And the claim is that I get the Schwarzian action. Okay, so in particular, we have to go to a limit where the boundary gets close to the boundary of ADS2. And you can't, it needs to be relatively smooth, right? You can't have the curve doing like weird things like this. It needs to be relatively smooth. So let's try to be a little bit quantitative about that, okay? So if we assume given some, so this curve is going to be parameterized by some proper Euclidean time L. Okay, so this curve is given by R as a function of L and phi as a function of L, right? So R and phi are these coordinates on H2. If we assume 1 minus R is small, okay, so R is close to being 1, which is where the ADS2 boundary is. And we also need to assume that this is relatively smooth. Okay, so the claim is that K, the extrinsic curvature of this curve, is given by the following formula: 1 plus R squared over 2R times cosine alpha minus alpha prime, where alpha is the angle between, okay, so let me draw this picture. Okay. So, okay, so phi is the angle. So I have some curve here, and at some point along the curve, it has angular coordinate phi. And we can think of the normal vector to this radius, right? We can think of that normal vector. And we can think of the tangent vector to the curve. We can think of the angle between the normal vector to the radius and the tangent vector to the curve. So, right, there will be a tangent vector, okay, some tangent vector. And we can think about the normal normal to the radius. And this angle phi, this angle is the angle that we're calling alpha. Okay, so if you go into the geometry of computing the extrinsic curvature, the curvature will be given by 1 plus r squared over 2r times cosine of alpha minus alpha prime. So alpha, okay, so this is the derivative with respect to the proper parameter along the curve. So if we assume that 1 minus r is very much smaller than 1, the curve is close to the boundary, and if we also assume that alpha is small, if we also assume that alpha is small, which means that the curve is very close to being a circle, right? So the curve is, if the curve is very close to being a circle, then this alpha will be small. Okay, so it needs to be kind of follow the boundary closely, and in this limit, this extrinsic curvature reduces to the Schwarzian expression. Okay. K, the extrinsic minus 1 is going to be given by 1/2 phi prime squared minus 1/2 phi double prime over phi squared plus phi double prime over phi. Okay. Okay, so phi is a function of L. Okay, and this is actually equal to the Schwarzian of e to the I phi okay, plus Schwarzian of phi with respect to L, and this is actually equal to Schwarzian of e to the phi L with respect to L. Okay, so this expression is actually equal to the Schwarzian of e to the I phi of L with respect to L. So we have that the JT action, because of the boundary term, reduces to the Schwarzian in the limit where the boundary is close to the ADS2 boundary. It reduces to, okay, so phi b here is the boundary value of the dilaton. Remember, we imposed Dirichlet boundary conditions. Okay, so phi b over 8 pi g Newton times dl times Schwarzian of e to the I phi L. Okay. So there's a minus 1. There's a minus 1 here. This minus 1 just gives a term that is constant when you fix the total length of the boundary. So fixing the total length of the boundary corresponds to, that's the path integral that we want to think about. We want to think about the path integral integrated over all curves with fixed length, total proper length. And in that integral, we can ignore that term because it's a constant. Okay, so does this look familiar? We had the Schwarzian action in the SYK model, right? And in the SYK model, we have the action, effective action is minus alpha Sn over J integral of the Schwarzian e to the I phi as a function of the proper time, not proper time, sorry, the physical time in the SYK model. So what is the correspondence between parameters here? We have the same action. The effective action in the SYK model comes from the action of JT gravity, and there's a correspondence between parameters. The correspondence between parameters is that, so remember, what are the two parameters in the SYK model? Large N and beta J. Okay? So, so just comparing the coefficient of the action, we get phi b over 8 pi g Newton is alpha S and over. Okay, so first of all, actually, we have to, there is a cutoff here. Okay, And the cutoff is the metric. We have to fix the metric, the proper metric on the boundary. So that's the Dirichlet boundary condition for the metric. And it's given by 1 over epsilon squared. Okay. And then the corresponding between parameters is beta j over epsilon. Beta j in the SYK model over epsilon is given by L over R, where L is the total length of the boundary curve in JT gravity, and R is the ADS radius. So I worked in units of R equals 1 throughout, but now I've restored the ADS radius. So the proper length of the boundary in units of ADS radius is equal to beta j in the SYK model in units of this cutoff epsilon. Okay, this is ADS radius. And alpha Sn over epsilon, so large n up to this numerical coefficient alpha s in units of epsilon is equal to the boundary value of the dilaton divided by 8 pi g Newton. Okay. So this is the correspondence between parameters and the SYK model and JT gravity. Okay, I think I'll end here.